best topology that is actually say for a particular problem of your interest. Okay, its generalization is very difficult actually. Okay, but still we'll come to that. That is, it is already proven that okay, you need to have only 2 hidden layers, okay, of sufficient number of hidden nodes in each of the such layers in order to represent, okay, most of the decision boundaries. Okay, because our ultimate aim is in building a multi-layer feed-forward neural network is we should have some say a form of decision boundary which will categorize our say the problems. Okay, the points. So that means it can be a straight line. Okay, it can be a parabola. It can be a third degree polynomial or 5th degree polynomial. 10th degree polynomial. Okay, so all this can be represented using 2 hidden layers and maybe hidden nodes. It's again we have to find out maybe trial and error, and also keep in mind that not too many number of hidden nodes we need to have such a output, okay, or such a result that we are actually expecting. Okay, learning the neural network structures. Okay, so there can be some issues like overfitting with respect to artificial neural networks. So overfitting is something like so for example, in this particular diagram, okay, assume that you are having a say points, okay, you are having so we are having say 1, 2, 3, 4 this one number of points. Okay, so the best fit is maybe suppose you are drawing a straight line through this one, that is one way, and maybe in this particular case assume that you have this particular say graph, okay, that is actually fitting. Okay, or you can say that you are drawing a say the line, okay, in this particular set of points you are having a straight line here. And you have one more say curve that is exactly going through these points. Okay. So the problem with the curve that is exactly going through this point is that that curve, that decision boundary actually will not generalize for future points, but a straight line which is maybe more or less fitting to most of the points, or which falls on goes through near to most of the points will be a better option. Okay, because that will generalize, okay, that will give a better prediction, okay, for future points. Okay, so this is actually maybe a case of overfitting. Okay, so exactly each of the what points are actually learned by the your model. Okay, and maybe when it comes to another point, a future point, your model will not be able to learn that one, okay, because it is not generalized. It is specific. It is learned for specific cases of each of the training samples. Okay, the general the common feature, okay, or the commonality that is existing in the training data is actually not studied by, learned by your algorithm. So that is called an overfitting problem. So NN has got an issue of overfitting problem. Okay, but there are workarounds also to avoid that overfitting problem. Okay, so that is how we have to connect the fully connected network. And so there are 2 ways in which you can maybe reach the architecture. So one way is actually you start with one hidden layer and one hidden node. Okay. So that means all the input nodes will be connected to the single hidden node. Okay, and then you will have say 3 output node. Then suppose your error is actually not the maybe the least one, lot of error, then what you can add one more hidden node in the hidden layer. Okay, so in that way from the scratch, okay, from the lowest number of hidden nodes you increase the number of hidden nodes, and whenever you have a threshold you have reached, okay, then you can say this is the optimal number of hidden nodes for this particular problem. Another one is you can start with a large network and you can unplug, okay, hidden nodes one by one. Okay, and you try to see what is error, okay, for each of the cases. So that's called a optimal brain damage algorithm. Okay, it begins with a fully connected network and removes connections from it. And which are the connections that you can connect safely, okay, that is not falling your error below a particular threshold, you can disconnect it. And whenever your error actually crosses a particular threshold point, you can actually just stop removing the connections or nodes from the hidden nodes. So because you cannot actually change the input nodes and you cannot change the output nodes. They are fixed. Okay, because how many attributes are given for the problem, that's fixed, and how many output nodes you are having, that's also fixed. So you can play only with the nodes in the hidden layer. So that is actually the how the architecture can be say taken. So this is actually the fundamental of artificial neural network. So so here the very important thing is back propagation algorithm and the activation functions. Okay, and maybe the topology, all these things. So with this, we will wind up with the ANN, and now we'll go to the support vector machines. Quickly, we will go through. Actually, this algorithm, this material I got from MIT. Okay. Website, because it actually explains the SVM in a easy way.